This video is going to show you how to perform a chi-squared test for independence. Consider this scenario. We're interested in learning if there is a relationship between gender and handedness. To test this, we take a survey of 500 people and record their information and organize it in a cross-classification table. We want to know, are gender and handedness independent, or is one gender more likely to be left or right-handed? Keep in mind that whenever we talked about probability, independence meant that the conditional probability of B given A is equal to the marginal probability of B. However, this works well whenever all of the probabilities are known. Whenever we're just taking a sample, we don't have the actual true probabilities. Samples are not perfect, but they should be relatively close to the true probabilities. So our solution here is going to be to test if the sample proportions for each gender are what we'll call close enough to conclude that the two variables are independent. The chi-squared test for independence involves a situation where we have two categorical variables with at least two categories in each. We collect data for both variables and organize it in a cross-classification table. What we do is we calculate the expected number of observations in each cell if the variables happen to be independent, and we'll compare the observed counts with the expected counts to test to see if the two variables are independent from one another. The chi-squared test for independence has a framework for the null and alternative hypotheses, just like the chi-squared goodness of fit test did. The null hypothesis reflects the notion that the variables are independent from one another, while the alternative hypothesis reflects the idea that the variables are not independent. And again, do not use this exact wording. Replace the phrase "the variables" with the actual variables that you're working with in the context of the problem. For this particular scenario, where we're looking to see if gender and handedness are independent, here would be the null and alternative hypotheses. The null is that gender and handedness are independent, while the alternative hypothesis says that gender and handedness are not independent. Let's say that after we survey our 500 people, we observe the following results. There are 30 people who are male and left-handed, 240 people who are male and right-handed, 20 people who are female and left-handed, and 210 people who are female and right-handed. Notice that we've organized the data in a cross-classification table. We can calculate the row sums by adding across the rows, calculate the column sums by adding down the columns. Our strategy for figuring out if gender and handedness are independent is going to be to calculate the expected counts if gender and handedness actually are independent. How many people would we expect to fall in each of these four cells if gender and handedness are independent? We'll compare the observed counts in the table with the expected counts. And so if gender and handedness are indeed independent, these counts should be relatively close to one another. In order to calculate the expected counts for the chi-squared test for independence, what we'll do is we'll first choose a row I and a column J from the table. The expected count for that particular cell, if the variables are independent, is calculated by taking the row sum times the column sum and dividing by the total sample size. This process gets repeated for each cell in the table, so we have a table full of expected counts to go along with our table of observed counts. Couple of notes here. Make sure you keep 2 decimal places in the expected counts. Many of these are not going to be integers. We don't want to round to the nearest integer. We want to be as precise as possible. And second, the row sums and the column sums in the expected table are going to be the same as the row sums and the column sums from the observed table. What we'll do now is calculate the expected counts. Up on top, we have the observed counts from the actual survey. On the bottom, we'll have our table of expected counts. Notice that the row sums, 270 and 230, as well as the column sums, 50 and 450, are the same in both tables. Now, if gender and handedness are indeed independent, the way that we're going to calculate the expected counts is by taking the row sum times the column sum and dividing by the total sample size for each of the 4 cells. So if gender and handedness are independent, we would expect 270 times 50 divided by 500, or 27 people, to be both male and left-handed. For male and right-handed, we would have 270 times 450 divided by 500, which gives us 243. For females and left-handed, we would expect 230 times 50 divided by 500, or 23 people, to be female and left-handed. For female and right-handed, we would expect 230 times 450 divided by 500, which gives us 207. The test statistic for the chi-squared test for independence is calculated in a very similar way as the test statistic for the goodness of fit test. Let's let R denote the number of rows, or the number of categories for variable 1, and we'll let C denote the number of columns, or the number of categories for variable 2. We'll need our tables of observed and expected values, and once we have those calculated, the test statistic is calculated by taking the observed value for each cell minus the corresponding expected cell, squaring the difference, and dividing by the expected value for that cell. We repeat this for each cell in the table and sum each of the individual terms. That gives us a chi-squared test statistic. It's going to follow a chi-squared distribution with R minus 1 times C minus 1 degrees of freedom. So for our example of comparing gender and handedness, our test statistic is going to have 4 different terms. The first term is going to come from the people who are male and left-handed. We have 30 people from the survey who were actually male and left-handed. If gender and handedness are truly independent, we would have expected 27 of them to be male and left-handed. So in the numerator, we have 30 minus 27 squared divided by 27 in the denominator. The second term is going to come from the people who are male and right-handed. We actually observed 240 people from the survey who were male and right-handed. If gender and handedness are actually independent, we would have expected 243 of them to be male and right-handed. So our second term is 240 minus 243 squared divided by 243. The third term comes from females and left-handedness. This gives us 20 minus 23 squared, observed minus expected squared, divided by the expected 23. And finally, our fourth term comes from the people who are female and right-handed. We actually observed 210 people who were female and right-handed. We would have expected 207 of them to be female and right-handed if the variables are independent. We square the difference and divide by the expected count of 207. Working each of these terms out gives us 0.333 plus 0.037 plus 0.391 plus 0.043, which is a final test statistic of 0.805. The last thing that we need to calculate from these tables are the degrees of freedom. Notice that we have 2 categories for gender, so we have 2 rows. We also have 2 categories for handedness, so we have 2 columns. This tells us that the degrees of freedom is going to be 2 minus 1 times 2 minus 1, which is 1 degree of freedom. And finally, we calculate the p-value, make a decision, and come to a conclusion. Using Excel, we'll find that the p-value is 0.3696. Since we're doing this test at the 5% level of significance, we'll fail to reject the null hypothesis since our p-value is greater than alpha. And so our conclusion is that gender and handedness are indeed independent from one another. Another way of thinking about this conclusion is that knowing a person's gender does not give you any information about their handedness.